We can check the volume as well.
Are you happy for them munching away on their food at the moment?
Absolutely.
That's fine then.
They can munch in the front row. Oh, you've done it already?
No.
Hello, welcome to our one of our autumn talks for the Centre for Climate Repair. The Centre for Climate Repair is about what we do if we fail to meet our emissions targets. So we know that COP30 is on at the moment in Brazil. COP30 is called COP30 because we've had 29 so far that haven't really managed to do what was originally intended, i.e. to get us off fossil fuels. And the Paris Agreement in 2015, COP21, it was agreed that we should limit global temperature rises to 1.5 degrees, and failing that 2 degrees. Well, we're on target to exceed even 2 degrees. The option seems to be this idea of net zero by 2050. So that net zero suggests that we're allowed to keep on emitting so long as we offset our carbon dioxide emissions, but offsetting isn't proceeding particularly fast either. So what we're doing in our Centre for Climate Repair is looking at how we can accelerate the carbon capture side of the equation. Jenna will be talking to us today about how the oceans, in particular kelp, can be used to draw down carbon dioxide from the atmosphere. Then Luca, and Jenna's based in the Department of Earth Sciences. And then Luca, who's a fourth-year project student here in the Department of Engineering, will be talking to us about how we can examine the reflectivity of clouds. So we know that clouds are kind of white, but how can we look at how white they are and the reflectivity of the clouds? And then, so the idea of today was to explore students' work. And so the third talk is a talk by Edmund Reardon, who's a PhD student here in the engineering department, but he's unable to be here in person, so I'm going to present his talk. Now, moving forward, we're going to have an event in this room on the 1st of December, which is a Monday, and it's entitled Good Cop, Bad Cop. And it's going to be a reflection on how did COP go? Did it achieve its aims, whatever those aims might be, and what new is there to talk about, and how optimistic should we be? So do come along to that. That'll be here at 1 o'clock on Monday, the 1st of December. And then moving forwards, we've got more events on Thursday lunchtimes next term. So do make sure you're on our mailing list. And we'll be around at the end of this talk at 2 o'clock if you've got any questions. It's a big room for a small audience, but that's just the way the rooms booking systems work in the department. But I think our experience was for good cop, bad cop, that this is a good sized room for that event. Please invite friends, anybody who might like to come to the event on the 1st of December. It's open to everybody, and it should be interesting. So, without any further ado, I'm going to hand on to Jenna Azimrat-Andrews, yes. Department of Earth Sciences, and it's that right-hand button, advances it, and I'll give you that.
Thank you. Perfect.
Excellent, good.
Hi, thank you all for coming. I'm Jenna Azimrat-Andrews. I'm a second-year PhD at Earth Sciences and also the Department of Applied Maths and Theoretical Physics, and I'm affiliated with Centre for Climate Repair. And I'm going to be showing you a brief introduction to my work in general, and then a display of what my fieldwork looked like over the summer, so to show you like what a summer of data collection looks like for a PhD in my field. So, brief introduction to me. This is my background. I have an undergraduate in biology with a specialization in marine conservation. I did my master's in environmental technology, which specialized in integrating solutions to climate problems with policy. And then I decided to pivot back from policy back to the science to try and see what can I do to use those skills moving forward to like be able to actually implement some of these solutions. And now I'm focusing on quantifying carbon removal potential of kelp farms and forests. I'm very lucky to have an amazing team. I think every PhD knows how important your supervisors are. I have 3 amazing supervisors: Sash Touch in the Department of Earth Sciences, John Taylor in Applied Maths, and then a third supervisor, Kristen Davis, in Stanford. And my Stanford team is who I work with for my fieldwork data collection especially as well. I also have a kind of like an older brother PhD student, Jago, who's working on the model that I'm using as part of my PhD project to validate and quantify carbon removal for kelp farms. We also have some other collaborators. Ocean Rainforest is a company that we use for data collection, so they have a kelp farm in the Faroe Islands and previously in California, but no longer. And I'm very excited to I think I've not announced to Hugh yet, but we officially have a direct collaboration with Ocean Rainforest, not only via the California universities, but also directly with Cambridge now, which is quite exciting. And the Faroese University, and then these California universities. So that's who I work with on the monthly basis. And then the idea behind my PhD is essentially that the oceans are a massive sink for carbon. In general, that's very widely agreed upon. We know that kelp forests in natural systems are responsible for a vast majority of carbon removal in oceans. And we're trying to see how we can utilize that as potential carbon sinking technology in the future as a remediation attempt to reduce the effects of climate change. Oh, God, sorry. And we're aiming to do that with a mixture of environmental data integration and modelling with ocean biome, which is a model that Jago's been working on for his PhD for the last 4 years, which is a kelp growth model looking at the fate of carbon after it takes out carbon from the atmosphere and then excretes it and exudes it into the ocean. And just a brief introduction to this is that we know that, like I said, that kelp farms have the opportunity to take out lots of carbon from the atmosphere, and the best way to test this has been proven to be numerical modelling combined with field trials, and that's where I come in. So numerical modelling is Jago's side of it. He's developed this model for kelp growth, and then I'm validating it and testing it against field trial data from a kelp farm that we have access to for monitoring. And then in terms of where would the carbon go, once you grow it into the kelp, obviously it gets absorbed into the kelp and becomes part of the biomass. Right now, it's in a very early stage of development in terms of researching like kelp as a sink for carbon sequestration. It really would only work right now if we sunk it into the deep ocean. It would stay down there for a period of like hundreds to thousands of years. We're not there yet, but I'm very lucky. I feel very lucky to be working on the team that's starting to investigate that as an option right now. Currently, kelp is not only natural systems does it get sunk in this way, but we would be looking, for my goal in the future is offshore kelp farms that sink, that are then sunk once they grow directly into the deep sea. Right now, kelp farming is an aquaculture mostly used for commercial processes, but that's where we're monitoring at the moment with the kelp farms to see like how much carbon is a kelp farm sinking in a commercial setting, just like as a byproduct of it existing, which seems to be quite a lot so far, which I'm excited about as well. And then introduction to my fieldwork. Like I said, our kelp farm is based in the Faroe Islands, which is between Scotland and Iceland, for those who don't know, so it's subpolar. I was very lucky to be there over the winter, like the midsummer night, so it was dark for about half an hour and then got light again, which was very, very cool. This is an aerial view of our kelp farm. It's quite big. It has 2 main stations, an upstream station and a downstream station. It's also quite unique in the fact that it's the oceanography and movement of water around that farm means it's downstream always of a salmon farm. Salmon farming is one of the biggest industries in the Faroe Islands, and we know also that they excrete tons of nutrients, and often in kelp farming, nutrients are the limiting factor in growth. So we've seen in this farm, it's been kind of really effective as both a cleanup technology for those excess nutrients from the salmon farm, and also it means that they don't really have, so far that we can tell, nutrient availability being a limiting factor for growth. So it's been really successful in this region, especially because the layout of the fjord means it kind of has a one-way flow. It doesn't really experience the effect of the tides changing the movement of water. It just kind of speeds up and slows down with the tides, which I think is really cool. I love fjordal oceanography, I like fjordal oceanography, but that's why this location has been particularly successful for this farm. To show you what kind of work I work with physicists, which is very tough as a biology student, as you can imagine, but they're all super smart and they make it very easy and understandable, which I really appreciate. So we have 3 main methods of data collection: biomass surveys, which I conduct with the team, and then I assist as a field assistant in the biogeochemistry and physical monitoring of the farm. So here you have a CTD rosette, which is measuring conductivity, temperature, and depth. From conductivity, you can infer salinity, and you throw this into the water. It takes measurements all the way through the water column, and you bring it back up. These tubes you can see on the outside are called Niskin bottles. They have these triggers, so they're like an open cylinder when you throw it in, and they trigger at different depths to capture the water at those depths, which is really cool. And then you can tell throughout the water column the nutrient availability, the dissolved organic carbon, inorganic carbon, and oxygen availability of that water at that depth. So that's one of the methods we use for data collection. And then not shown here, but shown later, is the ADCP, the acoustic Doppler current profiler, which allows us to look at current speed and movement of water around the kelp farm. So for anyone who works in data science, we have like literally a wealth, like a treasure trove of data from this experiment. And it's such a big team between 5 universities and a business. Like the data we're collecting at this farm is quite extraordinary. And I know that every time I meet my Californian team, we're all very excited to see like how it's processing, like how we've been processing the data. Like I feel very lucky to be part of this team for that reason. And then some of the data points we're looking at is kelp growth rates, and then pH, alkalinity of the water, like I said, light availability, light attenuation through the water, to see how deep, to what depth can the kelp grow successfully and how much light does it need to grow. I know that was a problem we had when we worked in California last year, is we don't think the kelp got enough light to grow successfully, so that project was not as successful as the one in the Faroe Islands, which we're finding out from new reasons from all of this monitoring. So it's important both to monitor these farms to not only see how much carbon is being taken out of the water as the kelp grows, but also to look at what makes a kelp farm successful. Like if we are going to implement this as a solution, where and what, where would be good for it and what does it need to grow well. These are just to take you through what I did this summer, because I think it's going to feel quite abstract. We say, oh, I did field work. What does that mean? What does it look like? I was in the Faroe Islands for 2 weeks in June, and the first week was taken up entirely by constructing these mooring lines. So these were lines about 50 meters long of wire held down by weights and held up by buoys that we placed in different locations upstream and downstream of the farm, also within the kelp farm. And these are going to be taking measurements for 3 months long. So we have to make sure they're durable. We have to make sure they're going to withstand the currents and the photodegradation from the light. And it was quite a mission to get these up and running, but it was super fun. We had literally hundreds of sensors all the way down these lines. And we had to program them, make sure they were working, make sure they were emitting the data they were meant to be emitting. And then this is me being Bob the Builder, assembling the lines together and making sure they weren't going to fall apart. And the go-to in oceanography is always more cable ties. Each of these things is very expensive, and if you lose it to the ocean, you're going to be in trouble. So whenever I was like, is this enough? No, more cable ties to tie on, which was quite fun. I spent a lot of time drilling with hose clamps, drilling stuff together, so that was really fun. And then you can kind of see, for perspective, how large these lines are. It was really quite a cool mission to be part of. And then on the right there is also the ocean rainforest base in Karlbak in the Faroe Islands. So we got to work with the team, with the farmers who are actually going out and monitoring this kelp every day and seeing what their days look like as well. And they're extremely accommodating. Can't express how welcoming these guys have been for us as well, which is really lovely. They let us construct these for a week in their lab, which wasn't quiet or unnoticeable, I must say. This is a video I think I could get to play of what deployment looks like. If I could try to do this. So you kind of only get one shot at this. It's quite high. It feels like quite high tension at the time. But you have to plan the location for the mooring, make sure it's in the best spot to collect data for 3 months that it can be, because once it's in, it's hard to pull out again, and you have to reset and reprogram all of the sensors. So it was quite a mission, but here we were able to lay out the line very smoothly. It went really well. This is the Ocean Rainforest Vessel, which is the first purpose-built boat for kelp farming. It has this amazing crane, which makes everything easier because kelp is heavy and lines are heavy. So we're lucky enough to be able to use that boat as part of this project. And then that's what the mooring line deployment looks like. And then for the second week, we looked at physics and biogeochemistry. And this is the ADCP I talked about earlier. So this went into the water, quite a delicate operation again. You don't want to lose it to the waves, but it also has to make sure it's running, make sure it's calibrated, and then make sure it's not going to fly off when the boat starts moving. So we deployed it off the end of the boat and then very slowly took transects up and down the kelp farm several times a day, basically trying to get a really good read on how the water flows through this farm so that when we're trying to model it later, we know exactly what to compare it against. Especially because, I didn't mention earlier, but the Californian teams have a model similar to Ocean Biome called MacMods. And there are a few groups doing this kind of work at the moment globally, and we had a decision to either work antagonistically and try and race them, to try and see who could develop the model quicker, or we could work cooperatively. So there's a PhD version of me in Stanford called Madeline, and she's essentially doing what I'm doing with our model at Ocean Biome. She's doing with MacMods, trying to validate it, trying to test it. And we are working for the final year of our PhDs. I'm probably going to be going to Stanford. I've been invited to attend, and then work with her to test the models directly against each other. So that's another example of amazing collaboration that I feel very proud and lucky to be part of this team with, to be able to do this kind of work with them. Anyway, that's the ADCP. On the right is the CCD rosette again. So this is sampling the water from the Niskin bottles. You can't really see, but there's a bucket full of glass tubes, and then imagine you're on this boat and it's like 8 degrees and raining and your hands are cold and you have to try and like not spill this water that was captured 40 meters below because you can't really get it back again. This is what fieldwork looks like in oceanography. It's quite tough and challenging, but it's extremely fun. If anyone's interested in getting involved, I'd love to talk to you about it afterwards. And then this was my time to shine, the time I got the physicist. I could get them all working with me with my biology for once, which was really fun. So everyone rolled up their sleeves and we started looking at a biomass growth survey for the kelp. So one thing that's standard practice in kelp farming is that you don't just lay out the kelp and grow it for one season and then take it out again. You have to harvest it and then it regrows, and you harvest it and regrows. It's kind of like if you grew an apple tree, you wouldn't take the apples after the first season of growth and just chop the whole tree down. You lay it out and you let it regrow over time. But the only thing is that this regrowth has not been quantified extensively yet in the literature, so that's what we're trying to do this summer, is to quantify the rate of regrowth post-harvest, so that when we're looking at how ocean biome models regrowth post-harvest, we can see if it compares accurately against the real data. So I conducted an experiment looking at 5 different locations of the kelp farm, upstream, downstream, in the center, to see also how the nutrient availability and the flow rates change, the rates of growth over time. And we harvested the kelp 3 times in June, July, and August, and measured the regrowth rates between those months over time, because we know summer period, in the Faroes especially, there's a lot of light availability, that's when the growth is happening. So this was us taking one of our samples. We had we had the regrowth experiments and also a standard that was not touched. That was really fun, also to get the physicists all working on my biology, which I really enjoyed, and they kind of were like getting hand slimy and like there's shrimp in your hair and you're like, oh God, this isn't like my nice little like thing I throw into the ocean, pull out and it's clean again. And I was like, no, it's time to get in the kelp. So that was really fun as well. And then this was my second biomass survey I did in July, and I was also very grateful to have a research assistant for this project, which was my first assistant ever. Her name was Nonna. She was a MPhil at the Polar Research last year. She was incredible. But we didn't do the physics this time. We just only went out to check on the growth from the harvest from the previous month. And this is a very beautiful photo of the kelp. I think it looks lovely. It kind of has an angelic vibe when the sun shines through it. But I was there in July doing this. It was a very quick turnaround. Another thing to know about oceanography and field experiments is that if you're on a boat, something will always go wrong. But we planned also for an extra day of contingency. And our first day was almost completely wiped out by issues with the crane and the boat generator not working and our captain oversleeping and being an hour late. And these things happen, but it makes a challenge more fun and interesting. And also if you plan for it, like we were able to do, luckily, it didn't affect our data collection massively, which was really good. The aim of my talk today is I want to show you what like field work actually means. And this is what it looks like. Things breaking, but in the end, it goes well. The team is amazing and very supportive, so I'm very grateful for them. And then that's my talk about my fieldwork this summer. Thank you for listening.
So, if we've got any quick questions for Jenna now, I just want to say huge thanks to Andrew Harmsworth, who's brought along some students from the Lee School across the road. Really wonderful to have you here. And any questions for Jenna?
Thank you for the talk. You mentioned the team being like a dream team. Just wondering how the team formed, and maybe any advice on if you're trying to come up with your own research pitch, how you might bring together lots of different university research groups.
So this team was about 5 years in the making. The Stanford team with UCSD and UCSB have been working on MACMODs for a while. And they've been in collaboration with Ocean Rainforest before, but they hadn't yet reached out to Cambridge. At the Ocean Science meeting 2 years ago, Kristen Davis whoops, and John Taylor met, and they've been talking about having a PhD to validate their models against each other for a while, but there hadn't been the right candidate. I was very lucky to meet John Taylor at that conference, and I fit the description of what he was looking for, so we were able to, I kind of slotted into a position that they had been planning for a while, with like the correct mixed background of like having fieldwork experience and also modeling experience with oceanography. I would say as a recommendation for finding like that dream team, extensive research. Reach out to previous students, ask them what their experience was. Sasha and John have an excellent reputation at Cambridge. I don't think I've heard bad things about them before. But I would say that in a PhD especially, you're signing a contract to work for and with a supervisor for 4 years. So it's important that you know that they're good and that they like you as well. So in a way, like, you're not only working for them, they're working for you to achieve your degree. So I would say communicate before, make sure you actually get on, and then I would say background check, ask the students how they've done in the past.
Cool, thank you.
Great, well, we better move on.
Yeah.
So thanks again. And Jenna will be around at the end to answer any further questions. Great, thanks again to Jenna. So Luca Lin is a fourth-year student in the Department of Engineering here, and he is doing his project on stuff to do with drones, and it's that right-hand button. There we go, and if you put that on, everyone will be able to hear you.
Okay,
Over to you, Luca.
thank you, Hugh. Hello, everyone. I'm Luca Lin. I'm a fourth-year engineering student here in the Department of Engineering, and today I've just begun my fourth-year project on polarimetric imagery for clouds for quantifying the effects of marine cloud brightening. And today I'll just talk to you about what my project is and what I expect to get out from it in about 5 to 6 months' time. So I'll talk to you, I'll tell you approximately what marine cloud brightening is and why is the measurement of cloud properties important and needed, and then what are the current techniques that can be used to to monitor the clouds, and then what benefits does drone bring into the cloud measurement, this idea, and what are my next steps and where I'm going to fly. So in this wonderful schematic is about the marine cloud brightening. On the left-hand side is aerosol cloud interaction physics, and those are a bit complicated. But what is marine cloud brightening? So in today's world, trying to mitigate climate repair, the first and most important thing is try to reduce greenhouse gas emissions. But on top of that, it would be very good for us to have some other ways to control the temperature rise. So one of those is marine cloud brightening. So the basic idea is to make the clouds more reflective, and we can do so by introducing more cloud condensation nuclei so that the water would condense onto more nuclei, forming more droplets. So the droplet diameter will be smaller and they'll become more reflective. And we do that by spraying seawater into the air. And I believe the Dante here is in the team that's doing some nozzle work and things like that. But there are relatively few field trips or a few experiments so far in the world. Like, for example, this one is Southern Cross University, and they did it in Australia for the Great Barrier Reef, but there aren't many other experiments so far. It would be good to have data. It's a bit messy, but it's okay. It would be good to have data that we can get data to validate the model and calibrate the model, because currently we have a lot of models that predict aerosol cloud interactions, but sometimes they give a large uncertainty. So with some data, we can make this more deterministic, and we will also be able to evaluate how well the marine cloud brightening is in some future experiments. And we can use this data to tell everyone, is it worth investing? And what are the benefits or risks involved with it as well? Okay, so this is what are the current techniques that could be used to measure clouds? So you could do in situ measurements. For example, you can send some probes into the cloud, or you could take samples of the cloud, but they lack representativeness, and you could sometimes have some sampling bias with it. Or you can take satellite and then do some satellite remote sensing. This has been developed for 30, 40 years. You can do that, but the spatial resolution will be lower, and then you have your thick layer of atmosphere between the cloud and the satellite. Some new approach, remote sensing using some research aircraft flying at about 30,000 feet, sometimes offer better results, and they give slightly higher spatial resolution, about 100 meter by 100 meter in one grid. But for early stage marine cloud brightening experiments, where a cloud of about 1 to 2 square kilometers is going to be altered or make brighter, the resolution is still not as high as possible. So there's a possibility that a UAV flying closer to the cloud can offer higher spatial resolution and see the change of the cloud reflectivity better. So how to do it? Flying directly into the clouds is not very safe or not necessarily legal. Or taking sample of clouds, again, has some representativeness or like sampling bias issue. But there's a way to just use polarized light. And basically, the idea is measure how the instant light gets reflected by the clouds, and the reflected light would behave differently based on the cloud droplet size distribution. And I would do that with a feature called cloud bow. The cloud bow is not as common as something like the rainbow. I believe, hopefully, all of you have seen rainbows that are quite beautiful. This is in West Cambridge, this is in Hong Kong, and that's in Bath. So the rainbows are basically when light goes into the rainbow and then bends and then reflected from the back of the droplet and then bends as it leaves the rainbow. And the different light bends by different amounts. So you can see this beautiful color. A cloud bow is very, very similar to the rainbow. The main difference being that the droplets are much smaller. So it still goes into the droplet and goes out. But the color don't get scattered, the colors don't disperse as much as the rainbow, so you see mostly a white ring. And on top of that, the cloud bow has a more pronounced scattering characteristic as well. So the idea behind the drone imagery is to take multiple pictures or videos of a cloud from different angles. For example, if this is a cloud, I'll fly on top of it, taking pictures at different angles. And this is a figure from literature that I refer to for my cloud measurements. So on the horizontal axis, this is a scattering angle. So the scattering angle is, imagine the sun is behind you and the light gets scattered back. So this angle would be the scattering angle between the instant light and then from where you take the measurement, basically. So the vertical axis is basically describing how the reflected light reacts, basically how the reflecting part or the scattering part would change the property of the light. And on the left graph, you can see the different effect on different effective radius. So the dark blue line is a very small effective radius, about 3 microns, and the light blue line has about 21 microns effective radius. And on the right, you can see the signal changing with different effective variants. So the idea is to measure the data and do basically a curve fitting. So I would generate a lot of theoretical results from me scattering theory like this, and then do curve fitting to the real data. And whichever curve fits is the best fit to my data, and then I can infer the cloud droplet size distribution that way. So this is one of the method called lookup table method. And there's another method which some of you might thought, okay, it might have something to do with Fourier transform. So Fourier transform is if you analyze a time domain signal and then you pick out their frequency components, basically turning a time domain signal into frequency domain. And there is something similar. About 10 years ago, someone said, okay, we could do something called the rainbow Fourier transform by turning the scattering angle domain signal into the cloud size, droplet size distribution domain. And that's something I will look into as well. So what are my next steps? So I will build a drone with polarization camera. Not this one, but it'll be of similar size. So that's one of the benefits that it could bring over a research-grade aircraft, because even if it's going to be a larger drone, it's still very portable. You can carry it anywhere you want, and it's cheap to fly as well. But I aim to have a relatively high scattering angle resolution so that I can do the curve fitting well, and especially for the rainbow Fourier transform part, I do need very high angular resolution. And these are basically some of the, yep.
I've got a question on the previous slide.
Yep.
You've got one that says sensitivity on effective radius and sensitivity on effective variance.
Yep.
I'm probably not the only person in the room who doesn't really understand the difference between those two.
Okay, sorry. So I think I missed out something. So the way that they generate these two graphs is by assuming that the cloud droplet size follows some specific distribution. And it's actually on the lower part of the graph from this paper, but I didn't include it. My apologies. But basically, it's a gamma distribution, and they assume that there's not a single radius, a cloud droplet radius, and it's actually sort of like spread out. So it's got some curved shape. It's like a Gaussian shape or like a bell shape, but it's not really a bell shape. But there's like a maximum for that distribution. So the effective radius is approximately where that maximum distribution happens. So the majority of the droplet would be around the effective radius. So that's the effective radius tells you about the size generally about the cloud droplets, and the variance is how wide this distribution is. Does it span from, for example, 1 microns to 10 microns, or does it span from only 6 microns to 8 microns? So that's two things in this graph. So by taking the measurements, I should be able to obtain both information based on the different shape of the signals. And yeah, so what are the next steps? I have to fly legally, so I need to rely on some temperature inversion. So I have spotted some very low-level clouds. This is in Scarborough last Christmas. So I have identified through literature and some online reviews, Google Maps, images, some of the possible sites I could fly this winter or early next year. The most important part would probably be the Peak District, Lake District, and Scarborough or Yorkshire region, because it's just like closer to Cambridge, and there are a lot of potential candidates scattered all in that small, relatively small region. And that's basically it. Thank you.
Shame you can't fly this in the room.
As
much as you'd like to.
Yeah, I break quite a few rules.
No, you're not allowed to break the rules. A quick question for Luca. It's going to have a lot of fun flying around with your drone. Looking forward to seeing the update when you're finished.
Yeah, sure.
Okay. So, let me talk a little bit about Edmund Reardon's project and the work that's going on in our seawater lab. Edmund is in the third year of his PhD, and he is making a nozzle, a spray nozzle, to produce little droplets of water. And if they are saltwater droplets, then as you can see, the droplets evaporate, and they will leave behind tiny salt crystals. So when the water's all gone, you're left with salt crystals, and those salt crystals make their way up into the clouds and help to nucleate clouds to brighten them. So the idea then is to take technologies that already exist and to try and understand them in terms of the droplet size distribution. Now, there's various groups around the world that have been working on this. Ahmed Neukemann in the United States, Daniel Harrison in Australia, Stephen Salter up in Edinburgh, and so we're building on existing knowledge. So here we have a steam nozzle. If you imagine you take a pressure cooker and you take the weight off the top of the pressure cooker, you get this jet of steam. Those droplets, turns out, if you've got a tube with high pressure and high temperature, the droplets come out of this pressure cooker nozzle, and it turns out that the the distribution of the size distribution of those droplets is really very suitable for what we want to do for marine cloud brightening. This is Edmund's rig in the lab. Down here is a B&Q pressure washer to get the high pressure, and then there's little heating tubes, heating elements to produce the high temperature. So it looks all rough and ready, but it's actually an extremely well thought through experiment. Now, what we then do is we take that spray of droplets and put it into a tube, suck these droplets through the tube, and as it goes through the tube, the droplets dry out, and at the far end of the tube, we've got this analyzer, the combustion analyzer, which looks at the dry salt crystals, and we look at the size distribution. And it's really interesting to analyze the size distributions because that tells us whether we've got the right device for brightening clouds. So here's our lab, and you know, it's what labs look like. They tend to be a little bit messy, but they do what they need to do. The main part, the clever part of the process is being absolutely sure that we're measuring the right size distributions of these droplets, because you can imagine that bits of droplets stick on the side of the tubes, or there are all sorts of ways you might lose droplets and not get correct size distributions, and that's what we're spending quite a lot of time working on. The tasks we've been trying to work on is getting size of droplets, 120 to 2,000 nanometer droplets. When they dry out, that produces salt crystals, which roughly divide by 4, because seawater is 3% salt, and volume goes as the cube of the diameter. So it works out, you divide roughly by 4. So 120 to 2,000 nanometer droplets gives rise to 30 to 500 nanometer diameter salt crystals. Now we want a narrow size distribution so we can target the size to be what we want. And we want to be able to control that size distribution by maybe changing the pressure or the temperature or the flow rates. We need lots of droplets, maybe out of one of these nozzles, 10 to the 15 droplets per second. A bunch of these nozzles, 10 to the 17. If we want to cool the planet, we might need 10 to the 22 droplets per second. Quite big numbers. And we've got to make sure that the energy consumption is not too great. So how are we going on all of this? The first thing we have to do is to be pretty clear that we've measured the right size distribution. This is dry salt crystal diameter on the horizontal axis, and it looks like it's got a peak somewhere a bit less than 100 nanometers. It's 70 nanometers, mode being the most popular result. The young people at the back of the room will know all the difference between mode and mean and median. Important stuff. So the particle concentration in droplets per cubic centimeter. And what we find is that depending on the temperature of the water and the pressure, we get a narrower size distribution. So it's quite a useful result, that. And then we look at how the spread, this narrowness, that's the geometric standard deviation, varies with temperature, and we notice that higher the temperature, we get a narrower distribution. And then this is the different pressures, different colors of the different pressures that we need to operate at. And then production rates, we want to decide how many droplets per second can we produce, and the higher the production rate, the blue colors of higher production rate. But then we're interested in particular size ranges. So the production rate of MCB particles. They're the ones that we really want. There's no point in producing lots of big particles. So as you can see, there's lots of trade-offs. So the blue is high production rate, but not really of the particles that we want. The particles that we want up on the top right, it's relatively low flow rate. So it's all heading towards the idea that high temperature is a good thing, which is very neat. So we know we're doing the work trying to figure out what temperatures we need. The other interesting thing is power consumption. So this right-hand graph shows power for 10 to the 15 droplets per second. And we want low power. And again, the high temperature looks like it's useful. So we want to have high temperature, but we want to have a low flow rate. So anyway, this is what Edmund's work is all about, and trying to keep the power low. Now, so where have we got to? We've done pretty well in controlling the size distribution, so we kind of crossed that off our list. We've done pretty well in getting a narrow size distribution. We're getting there on controllable size distribution. We pretty much know how we can produce 10 to the 15 droplets per second. But as for wider use, well, these are the devices that they're using in Australia for marine cloud brightening on the Great Barrier Reef. We haven't quite got to the scaling up stage yet, but that's what they're working on now. So we need to do a bit more work on the controllable size distribution and on the scaling up. I'm just going to move on now because I'm just a bit short of time. The actual tests we want to do involve having some kind of array. Do we want to scale up? We don't want to have just one nozzle. We want to have 100 parallel nozzles in some kind of array. But one of the things that we're thinking about there is that do these nozzles, do the droplets bump into each other? Do we get what's the effect of having 100 parallel jets all nearby each other? And that's what Edmund is working on at the moment. The particle size distribution, I apologise being Edmund's slides. I'm doing my best here. I'm going to move on just because I want to. There's other work going on in our lab, which is about other methods for producing droplets. And this is a rather neat approach. It's called the electrospray technique. And the idea is that if you have a tube, that tube on the right-hand side is about 1 millimetre in diameter, half a millimetre in diameter. It's like a syringe, a needle from a syringe. If you have a 10,000 volt potential difference on that and put salt water coming out of that, the 10,000 volts attracts electrons, get attracted to the droplet, and the droplet gets stretched out, and you get this tiny little point, and that point has got millions of electrons on it, and it disintegrates into a stream of tiny droplets. And it turns out that those droplets are just the right size for marine cloud brightening. And so one of the advantages of this technique is that it's got different controllability knobs. Voltage is the key one. So we're working on that. And what we're finding is that the droplet size distribution is fine, but scalability might be a bit of a problem. How can we scale it up to 10 to the 17 droplets per second? Another one we're doing in our lab, Yashas Raj is a second-year PhD student. He's got this thing which he likes to call the bubbleizer. And this is basically a rubber tube with little holes in it. and you put compressed air into the tube, and it produces bubbles just on the surface of the water. So you don't need any fancy bits of kit. You can imagine having a tube just out the back of a boat, put compressed air into this tube, and it foams up the surface of the water. And it turns out that the little bubbles, the little droplets that get formed, are again just in the right range for marine cloud brightening requirements. The nice thing about this technique is that you're not putting liquid through the little holes. It's just air, which means you don't have to worry about filtering, because the sea is full of crud from fish poo and bits of plankton and things. If all you need to do is blow air through these tubes, then that makes life a bit easier. So that's Yashas's work. And the general experimental setup is that we have so for Yashas, we've got a nitrogen tank blowing air into his little rig, but then everything else is the same as for all of our experiments, measuring the droplet size distribution. So that's what our lab has got, whatever device it is that you're using to measure the droplets, to make the droplets, and this is Yashas's bubbleizer, but then it goes off to the measuring techniques. This is the kind of summarizes things. We've got the Rayleigh jet, which is another technique for generating droplets, where we take when you turn the tap on and the water comes out of the tap and it produces droplets. Well, if you did that on a micron scale, you can produce little droplets. And so the Rayleigh jet distribution gives us some, it's another technique. And if we start to look at the distributions from the different techniques, then, we've got to decide which is our preferred technique. It depends a little bit on how the quality of the water matters as well. So anyway, this is all research in progress. I'm mindful of the time. I'm going to wind up, hopefully, here and say thank you very much for coming along. I won't take any questions now because we do have to vacate the room ready for the next lecture at 2 o'clock, but we'll gladly stay around and answer questions to those who would like. So hopefully we will see you, if not on the 1st of December, we will see you at our talks next term. Keep your eye out for them. Thank you very much.